Hello and welcome to the third lecture in this series on Introduction to Finite Field for Error Control Coding. My name is Smith Kumar Chaube and today we are actually going to start our discussion on finite field. But before we do that, let's quickly review some of the concepts that we have learned in the previous lecture, namely group and field. So let's start with the group. So a group is generally a doublet, a set G together with an operation star, and in general this operation star can be either addition or multiplication. So this doublet is going to be a group if it is going to satisfy certain conditions, namely closure. It means that under this binary operation star, this group must be closed. What I mean by that for all AB element of G, A star B should be also in G. It must satisfy associative law. What I mean by associative law is that A star B star C should be equal to A star B star C. So it doesn't really matter which operation you do first, result is going to be the same. Then there must be an identity element E in the group such that A star E is equal to A or E star A is equal to A. Now for each and every element in the group, there must exist another element A dash in group, and this A dash element is called inverse of A such that A star A dash is equal to E. In general, group doesn't need to be what we say commutative, that A star B should not be in general equal to B star A. But if it is going to be satisfied, then our group is called associative group or abelian group. Now let's move on to the field. So field is basically a triplet. What I mean by triplet is that there is a set F, operation addition and multiplication, and this triplet is going to be a field if and only if multiplication is distributive over addition. So multiplication must be distributive over addition. At the same time, this group F with operation addition must be a commutative group. So this must be a commutative group, means it should satisfy closure, associative, identity and inverse. Apart from that, it should also satisfy commutative law. And non-zero element of F together with this operation multiplication, so F cross means basically non-zero element of F together with the operation multiplication should also form a commutative group. So it means that there must be a closure, associativity, identity and inverse. And identity element with respect to addition is called additive identity or zero element. So zero is going to be our identity element. It is called generally zero element or additive identity. In the similar manner, 1 is called unit element, or it is also called additive multiplicative identity. Okay. Then there is something called order of the field. Order of the field is number of element in the underlying set F. So if number of element in set F is finite, then that group is called finite order group or finite group. Finite order field or finite field. So a field in which the number of element in the underlying set F is finite is a finite field. This is the field that we are going to discuss in today's lecture. But before that, let's quickly review some of the notation. That minus B is simply the additive inverse of B, and B to the power minus 1 is multiplicative inverse of B. This is just for the notation. Now let's move on to the Galois field or finite field. So Galois field is a field in which the number of element is simply finite. So if the number of element are finite, then the field is called Galois field or finite field. And it is, let's say that number of element is Q, then the field is called GFQ, means Galois field Q or finite field Q. So let's see some of the example of finite field, but this example we have already seen in the last lecture. Here in the underlying set we have 0, 1, 2, 3, 4. So we have 5 elements in the underlying set, and this is actually when you divide any integer by 5. So this is also written as z divided by 5z. So this is, and the operation of addition is modulo 5 addition. So if you add two elements and if the addition is greater than or equal to 5, you divide it by 5, and whatever the remainder is, that is going to be our result. Similarly with multiplication as well. So to prove that this is a what you can say, it is a finite field, we have included two of the Cayley tables. So we have one Cayley table here and another Cayley table here. This is with respect to modulo 5 addition, and this is with respect to modulo 5 multiplication. Now in this additive Cayley table, you can see that in each and every column the elements are all different. For example, here all the elements are different, here all the elements are different. No two elements in a column or in a row is equal actually. Okay, so it means that it is going to satisfy closure. Apart from that, it is also going to satisfy associative law. Identity element with respect to modulo 5 addition is 0, and since 0 exists in each and every row or each and every column, you can say that inverse exists for each and every element. So inverse does exist for each and every element, and it is going to be commutative as well, because if you take the principal diagonal, then this each and every element here, for example 1 is here, then you have another one here. If 2 is here, then 2 is here. So this matrix is actually symmetric. So if it is a symmetric matrix, then group is going to be commutative as well. So it's a commutative group. Now here in this case we are not going to consider this 0 or 0, because we are going to consider only non-zero element, namely 1 to 4 here and 1 to 4 here. Okay, again our multiplicative identity here is equal to 1, and it exists in each and every column. That means that inverse exists for each and every element. Okay, all the elements are 1, 2, 3, 4 only, so there is closure. It's going to satisfy associative law, and it's also commutative, as with respect to principal diagonal it is symmetric. So if you consider principal diagonal here, then all these elements are symmetric. If you have 3 here, in the similar position you have 3 there. Okay, if you have 4 here, then in the similar position you have 4 here. If you have 1 here, then in the similar position you have 1 here. So it's a commutative group under multiplication. So we can say, now the last point is that it has to be multiplication should be distributive over addition, and in general arithmetic multiplication is actually distributive over addition. So in modular arithmetic it is also going to be the same. So that's very trivial to prove. You can do that, and we can say that this is actually a field. And we have also seen that for any prime number p, if you have a prime number p, then a group z divided by pz actually forms a field. So if you have if you have a set F which contains z pz, then it is under modulo p addition and multiplication is going to be a field. Okay, where p is a prime number. So here 5 was a prime number. Now some of the properties of the field that we have already seen, that for every element a times 0 is equal to 0. If a and b are non-zero element, then their multiplication cannot be equal to 0. And if you have two elements and their multiplication is equal to 0, and one of those elements is not equal to 0, it means that second element must be equal to 0. And this is generally follows from the arithmetic. And then there is cancellation law, that a times b is equal to a times c, and a is not equal to 0, then there will be cancellation of a on the both side, and you will get b is equal to c. So let's move on to the characteristic of finite field. So before we discuss that, we have to remember that number of element in a finite field is finite. What we mean by that is that under addition, this is going to be finite. So the result can be only q values. If you add any value any number of time, its result output is going to be q only, right? Only q output can be there. So if you have 1 as the unit element in the GFQ, then summation of I is equal to 1 to m1 must be equal to summation of I is equal to 1 to n for some m and n where m is less than n. This means that I is equal to 1 to n minus m, 1 is actually equal to 0. So there must exist some positive number lambda, and let's assume that it is the smallest positive value, for which this summation I is equal to 1 to lambda 1 must be equal to 0, and this is actually called the characteristic of the field Q. So the smallest positive integer lambda for which I is equal to 1, summation I is equal to 1 to lambda 1 is actually equal to 0 is called the characteristic of the field GFQ. Now the characteristic of the finite field is always going to be a prime. It's always prime. If it is not a prime, then lambda can be written as multiplication of two prime number of simply two numbers. Then if you take this summation times this summation, this will be equal to I is equal to 1 to km1, and this is actually equal to lambda, and we have already seen that this is equal to 0. What we mean by that this time this is equal to 0, let's say this is A, this is B, then either A should be equal to 0 or B should be equal to 0, right? It means lambda cannot be smallest positive value, for which this is 0, this summation is 0, right? That contradicts our definition that lambda is the smallest positive integer. What that implies is that our assumption that lambda is not a prime number is wrong. So lambda must be a prime number. Now next we have some of the feature of this lambda. Okay, now all these summation from 1 is equal to I is equal to 1 to 1 1, and then another summation I is equal to 1 to 2 1, and all these summation with unit element should be distinct, because if using the previous, or what you can say, this is always going to be different, right? Okay, so these distinct element actually form a group under the actually form a field under the addition and multiplication of GFQ. So this GF lambda is called the subfield of GFQ, and if Q is not equal to lambda, we know that every field is a subfield of itself. So if lambda can be actually equal to Q, but if it is not equal to Q, then Q must be equal to some power of lambda. For example, lambda, it may be lambda square, lambda cube, or something like that. So it can be in general lambda k, where k is element of integer, okay, or a positive integer, let me say. So k is element of positive integer, okay. Now let's consider the order of a field element A. So let's say that we have a non-zero element A in the Galvez field, and then the power of A means when we are taking power, we are actually multiplying A with A, right? So non-zero element of the field is actually closed under multiplication, isn't it? So this must be all non-zero element in GFQ. Since GFQ has only finite number of element, there must exist two positive integer k and m such that a to the power k is equal to a to the power m. In this, that means that a to the power m minus k is equal to 1. So there must exist some smallest positive integer n, let me write it like n, for which a to the power n should be equal to 1. So when a to the power n is equal to 1 and n is the smallest positive integer, then n is called order of the field element A. Okay, so all these power a square, a cube, all the way to the power a to the power n and an are all distinct. They are all going to be different. And after that, if you take a to the power n plus 1, you are simply getting a to the power n plus 2, you are simply getting a square. So it is again going to repeat itself, right? So using this a, you can actually form a cyclic group under multiplication of GFQ. Okay, and we say a group is cyclic when each and every element of that group can be produced using only one element. Okay, now here is a theorem that for any non-zero element A in GFQ, a to the power q minus 1 is always equal to 1. Okay, a to the power q minus 1 is always equal to 1. So if you are considering GF5, then 3 to the power 4 must be equal to 1, 2 to the power 4 must be equal to 1, 1 to the power 4 is actually equal to 1, and 4 to the power 4 is also going to be equal to 1. So this is what we mean by this, that for any non-zero element in A in GFQ, a to the power q minus 1 is always going to be equal to 1, and it's actually very easy to prove. Let's say that there are q minus 1 non-zero element and those elements are b1, b2, bq. So if you multiply them together, their result is going to be something, right? Let's say that value is x. So if you multiply k distinct element of the field GFQ, then you are going to get some element. So again, if you have a, then a times b1, a times b2, a times bq minus 1 are all going to be non-zero element, isn't it? And they are all going to be distinct. So if you multiply them, you must get the same value. So this must be equal to this. Or if you simply change the order, you will get a to the power q minus 1, b1, b2, bq minus 1. Here again b1, b2, bq minus 1. And using the cancellation, this will be cancelled out with this, and you will get a to the power q minus 1 equal to 1. Okay. Now, if n is the order of non-zero element A, then n must divide q minus 1. Okay. If it is not dividing it, let's assume that n doesn't divide q minus 1, then there must be some remainder. So q minus 1 must be equal to n times k plus r, where r is less, r is between 0 and n, and it should be actually less than n, isn't it? So a to the power q minus 1 actually becomes a to the power kn plus r, or a to the power n time k, and this value is actually equal to 1, isn't it? Because n is the order of the element A. So you have a to the power r that is equal to 1. So a to the power r becomes equal to 1, and that actually contradicts our definition that n is the order of non-zero element A, because now r is less than actually smallest value, isn't it? And n should be smallest value by its definition. So it means that our initial assumption that n doesn't divide q minus 1 is incorrect. So n must divide q minus 1. So these are the two theorems that one has to keep in mind. Okay, now we are going to move on to the primitive element of a finite field. And a non-zero element A is said to be primitive if the order of this element A is actually equal to q minus 1. So let's consider 4 here for example. So you will see that 4 to the power 1 will be equal to 4. 4 to the power square, 4 times 4. So you see it's 4 here, and this is 2. So this must be equal to 2, isn't it? Then 4 cube is actually equal to 4 times 4 square, or 4 times 2, isn't it? The 4 times 2 will be equal to 1. So this becomes 1. So 4 cube is equal to 1 here, and so order of this element 4 is actually equal to 3, but it is not going to be a primitive element because 3 is not equal to q minus 1. Here q is 7. So if this was equal to 6, then it should be a primitive element. Now let's consider another example here, 3, right? So 3 to the power 1 is equal to 3. 3 square will be equal to 3 times 3, and you see that it is equal to actually 2. And then 3 cube will be 3 times 2, and that will be equal to 3 times 2 equal to 6, right? And then we have 3 times 4, that is equal to 3 times 6, and 3 times 6 will be actually equal to 4. So this becomes 4. And then 3 times 5 will be equal to 3 times 4, and which is equal to 3 times 4 is actually equal to 5. Okay, from the table itself you see that 3 is here and 4 is here, and their multiplication is here, so this is equal to 5. And 3 to the power 6 is actually 3 times 5, and that is actually equal to 1. So you see none of these power are actually equal to 1 except q minus 1, that is 6. So 3 is a primitive element of this set. So 3 here is a primitive element of the set, and primitive element, there may be more than one primitive element. Actually there are generally more than one primitive element in the finite field. So now let's discuss something about the primitive element. The power of the primitive, if you have primitive element, then we have seen already in the previous example that using its power you can generate all the non-zero element of GFQ. So using primitive element we can generate actually all the element of GFQ, and every finite field has a primitive element. This is a must, that if you have a finite field, then there must be a primitive element there. And non-zero element is a finite cyclic group under multiplication. This is something that we have already discussed. And the number of primitive element in GFQ is given by phi q minus 1, where phi is the Euler's function, or actually it is called totient function. So Euler's totient function phi n for input n is the count of number in 1 to 3 n that are relatively prime to n. So we have to simply count how many number are prime to n, and that will be our phi of n. So for 7, so phi of since q is equal to 7 and we are taking phi of 7 minus 1, so phi of 6, to calculate it, phi of 6 we have to simply write down how many, 6, 5, 4, 3, 2, 1. And in this set you see that with respect to 6 the relative prime is 5, 4 is not relative prime, 3 is not relative prime, 2 is not relative prime, and 1 is relative prime, right? So 6, 5 and 1, these two are the relative prime number with respect to 6. So the phi of 6 is equal to 2. If you consider another example, for example q is equal to 5, this is also a field that we have seen. Okay, so in this number of a primitive element will be phi of 4, and phi of 4 we have to simply count 4, 3, 2, 1, how many of them are actually relative prime. So 3 is relative prime and 1 is relative prime, so this is again equal to 2. So using this Euler's function phi n, one can calculate how many primitive elements are actually there in the field. Okay, so if you have any comments or if you have any question, you can put them in the comment box. Thank you.